Welcome to my presentation on infrared free electron lasers, their applications and science examples. So here's a brief outline. First, I want to bring you a bit into the field of low energy excitations in solids mainly, so the physics that we want to look at with the infrared free electron lasers. Then we will have one example from chemistry or molecular physics where ion mass spectroscopy is used with a free electron laser that is in a macropulse mode. And then we will stay mostly with examples done here at Helmholtz-Zentrum Dresden-Rossendorf at Felbe, at the Felbe facility. And there will be examples where we use a free electron laser for pumping the samples and then use various probe techniques to see what's happening. And towards the end, I will introduce to you quickly what superradiant sources are, what their advantages and disadvantages are compared to free electron lasers. All right. So here you can see the full electromagnetic spectrum, starting from microwaves at very low photon energies and going up to X-rays, where many of the presentations with free electron lasers, a lot is done in this region. We are using free electron lasers in the infrared and terahertz region, and there's this terahertz gap, which is loosely defined by the region of, say, 0.3 terahertz to 30 terahertz. The boundaries are really not strict. This depends a bit on the community you're talking about. But one thing, why is this gap? Or what do we mean by the gap? Well, this is a lack of technology, because from the low frequency side, electronic sources are well established and can work perfectly. And from the other side, photonic sources, lasers, can work very well. And you see, for all spectral regions, basically we have everyday examples that we use in our daily lives, such as CVD players or car collision radars, microwave ovens, mobile phones, and of course in medical X-ray imaging. In the terahertz, we're not so familiar with systems. Now communication is coming up, and some security systems at airports, they work at 0.1 terahertz basically. In the laboratory, we have many terahertz sources. This is well established, but still powerful sources for certain parameters are not so easy to achieve. So this is a range where free electron lasers still play an important role to cover the spectral range. What can we look at? In solids, there are various quasi-particles such as magnons, plasmons, polarons, superconducting gaps, phonons, so vibrations of a crystal lattice, and in molecules where similarly vibrations, or at lower energies, rotations or vibrations of very large, typically biomolecules. With a free electron laser, infrared free electron laser is an source that provides intense, tunable, narrowband sources. And with this, we can resonantly drive with excitations and do nonlinear spectroscopy. So we cannot just see the excitations in a static spectrum, but we can strongly excite them and basically change the properties of matter by this resonant excitation. Very quickly, the basics of a infrared free electron laser. It consists of an undulator where the electron beam is sent through, and then radiation is created, and it consists of a very simple cavity with one end mirror and one mirror with a hole where part of the radiation is coupled out. And so, as mentioned before, they cover the mid-infrared and terahertz region. Pulses typically have a duration of picoseconds, and pulse energies are in the microjoule range. Now the mode of operation depends on this electron accelerator here. Many free electron lasers operate in a macropulse mode, so this looks like this, that where individual pulses that are like, for example, 1 nanosecond apart. This is the structure of a Felix free electron laser in the Netherlands. Very similar is the Clio facility in France, also a user facility, and at Fritz Haber Institute in Berlin, there's also a similar laser, but it's not a user facility. So where this pulse is emitted, and when such a pulse train is a few microseconds long, and when there's silence over 100 milliseconds, so with a 10 Hertz repetition, rather low repetition rate, these macro pulses are repeated. At Felbe in Dresden, we have a different mode of operation because we have a superconducting accelerator, and this allows for CW operation. CW here means continuous pulsing, so it's the language of the accelerator people. It's not CW radiation, it's a continuous pulsing. And for us, the repetition rate is 13 megahertz, corresponding to 77 nanoseconds here between individual pulses. Before we look at example experiments, let's quickly discuss how one would come from an idea to results at such a free electron laser. Well, if you have an idea, think about it. Maybe you have some preliminary results like static spectroscopy data, and then discuss with a beamline scientist if this could work well at a certain facility, and then submit a proposal. Typically, the user facilities have 2 calls per year, and then proposals get evaluated by an external panel. If you get the beam time, then one has to work out a detailed plan, and before the shifts, test and align everything. An essential part in a typical pump probe experiment is finding the spatial and temporal overlap at the sample position. Ideally, one would have a reference sample that is known to give a strong signal for a given technique, and then one can do the experiment. Hopefully it's successful, and the results can be published. So a typical campaign at the Felbe facility would be something roughly like 5 shifts, and each of them be 12 hours. And if this works well, this can already give a very good paper. So here's the first science example. It's from a Felix free electron laser in the Netherlands. So where there's this macropulse structure, and if molecules are resonantly excited, the lifetimes were very long. So basically the energy piles up within the macropulse. So something like 10 millijoule of the macropulse can be dumped into these molecules, and this means the vibrations are strongly excited, and finally the molecules will break and fragment, and then these fragments can be collected with ion mass spectroscopy. It's a very sensitive technique, so one can work with very small sample volumes, and since it's a dynamic process, one can look into this dissociation dynamics. So we're looking at various interesting samples, like samples from out of space for some astronomy questions, and some designer drugs are evaluated where to, this is with the Dutch police project, where new dangerous substances are identified by this very sensitive technique. Now let's come to the experiments at the Felbe free electron laser, and let's start with the simplest technique, namely single color pump probe. So in this case, one would simply split the beam of a free electron laser by a beam splitter, have a stronger pump pulse on the sample and a probe pulse that is time delayed by such a movable mirror stage, and then one looks at the transmission, or could also do in reflection geometry, how the sample responds to this pumping. As an example, some years ago, we looked into graphene, so monolayer of carbon that has this Dirac-like band structure. So we pumped at different energies, but always the pump and the probe energy was the same. And we excited electrons from the valence to the conduction band in this Dirac cone, and then there's Pauli blocking of these electrons, and one gets an increase in transmission because of this Pauli blocking, and then a characteristic decay time, and we found that the decay is significantly faster for larger photon energies than for smaller ones, and this can be understood because for the larger photon energy, there's a chance of the electrons to emit optical phonons, and whereby they can quickly relax, whereas at lower energies, when they keep their energy and the transfer to the crystal lattice is much slower. So this is experiment, this is theory. Let's go one step further. So in the previous example, the radiation changed the occupation of the energy states, but the band structure, the energy states itself, was not changed by the radiation. So this was perturbative nonlinear optics. If we pump a system very strongly, so beyond the perturbative limit, we can change actually the energy structure. And the simplest example is given here. It's a two-level system with a resonant optical excitation. So if we have such a system, initially the ground state would be occupied by electrons, the radiation comes in and excites to the upper state, but then de-excites. So there's this, in the time domain, this cycle of Rabi oscillations. If we look at the same process in the frequency domain, this means that these two energy levels split up. This is called AC Stark splitting or Outlet-Hahn splitting. And the energy of this splitting is proportional to the electric field and the dipole moment of this transition. So this is h bar omega Rabi, this Rabi frequency that we saw in the time domain. So what we have here is actually a mixture of electronic and photonic nature of these energy levels. So it's called dressed states. Like here, without the optical excitation, of course, it's purely electronic matter, and then we dress these electronic states by the light and arrive at the new states. The sample, the model system we use to study this is inter-subband transition in 3-5 semiconductor quantum wells. So it's depicted here, a gallium arsenide quantum well embedded in aluminum gallium arsenide. So the aluminum gallium arsenide has a larger band gap, and this forms a quantum well here where electrons and holes can sit in this quantum well. So they can move freely along the plane of a quantum well, but are confined in one direction. And if we have transitions, optical transitions across the band gap, so from a valence band to a conduction band, these are interband transitions. These are exploited in diode lasers, but one can also have transitions between, just within the conduction band. These are called inter-subband transitions, and this is used for quantum cascade lasers. This is a very successful technique to create mid-infrared and terahertz radiation. So the setup for this experiment looks rather complicated. I don't want to go into the details. This is basically the probe scheme. So we use a near-infrared femtosecond laser, photo-excite some nonlinear crystal. This generates the terahertz. The terahertz radiation, broadband terahertz radiation, is focused on the sample and then is detected by a scheme named electro-optic sampling. With this technique, we get amplitude and phase information in the time domain, and this can be converted to in the frequency domain to the complex dielectric conductivity of the sample. Now, in addition to this broadband probing, we bring in the free electron laser for narrowband pumping, for resonant pumping of these intersubband transitions. Here are the results. So the gray curve is without the free electron laser. So here we probe with lower intersubband transition. Now, if we turn on the free electron laser and pump with upper transition, it splits, and this can be seen here in the red curve. This is the outlet down splitting, and there's a bit of a redshift due to heating. We can do the same experiment, pumping and probing the upper transition when there are these four possible transitions indicated by the blue arrows here, and this makes a splitting into a triplet. This is named the Mollo triplet, and in fact this result here is the first observation of this Mollo triplet in a solid state system. You see the lines are rather broad, they merge together, but it's showing you this technique, the broadband probing, and the type of physics we can look at, the really non-perturbative nonlinear optics. The next example is about tiny light emitters, namely excitons and tryons in 2D monolayers. So where materials like molybdenum diselenide, where a monolayer is a direct semiconductor, and excitons as an electron-hole pair, so the equivalent to a hydrogen atom, and tryons, so 2 electrons, 1 hole, a 3-particle system equivalent to a hydrogen ion. These can form in this material, and they can recombine and emit light. And this is shown here. This is a strict camera image. So on this axis is the photon energy of the emitted photoluminescence. We see the exciton very bright here at a bit higher energy, and the tryon a bit dimmer at a lower energy. And the tryon lives longer. So this is the transient here in the time domain. And the exciton decays quickly. So this was well known, and people showed that one can switch between tryon and exciton emission by forming a transistor-like structure where with a gate electrode one can electrically switch between the two states. So we ask ourselves, can we switch quicker? Can we switch on ultra-fast timescales by doing it optically rather than electronically or electrically? What did we do? Well, in addition to exciting these tryons and excitons by blue light, we came in with the free electron laser, and we used the photon energy of 29 millielectron volt, which is about the tryon binding energy. What happens? So here's without the free electron laser, we see basically the picture like before, the long-living tryon emission, the shorter living exciton emission here. And now in this view graph, at the temporal position of this dashed line, we come with the free electron laser. What happens? The tryon emission gets dimmer, it gets quenched, and the exciton transition lights up. So we can brighten this transition. It means we shuffle from the tryon to the exciton. We quench the tryon and we brighten the exciton. So it means it's a dissociation of the tryon. We remove this one electron and convert the tryon to an exciton. Here is shown how this transfer ratio depends on the photon energy. So we tune the free electron laser, and we see for small photon energies, when we are below the binding energy of the tryon, not much is happening, and when it really goes up, when we exceed the binding energy, and when it's going down again, and theory can explain this very well. That it goes down, this has to do with the excess of kinetic energy one has to get rid of, so the process becomes less efficient. Okay, so let's summarize what we have seen so far. So we have a tunable narrowband radiation that is very good for high spectral resolution and resonant excitation. The short pulses give us high temporal resolution, and the high intensities allow us to do high field physics, so nonlinear physics beyond the perturbative limit. But how about spatial resolution? Remember, 1 terahertz corresponds to a wavelength of 300 micrometer, so very large. And this, by diffraction theory, this is basically the limit of spatial resolution. Is that the final limit? Is there anything we can do better? Indeed, there is. There is a technique called scattering type near-field microscopy, SNOM. And what it is, technically, the instrument is an atomic force microscope combined with optical excitation. So it's depicted here. So this is the tip at the vibrating cantilever of this AFM. And when light is coupled in and the backscattered light is connected. So for this technique, the spatial resolution now is determined by the radius of this tip, because the light field is confined in this region and we can extract spectral information just from this region underneath the tip. This comes at a price that the intensity is very low and one has to typically fight with signal-to-noise ratio to get good pictures. And one can do this spectrally resolved. So we have a commercial instrument that uses a broadband mid-infrared source and a Fourier transform spectrometer. So we can, in the mid-infrared spectral range, get an image, a hyperspectral image, basically on the nanometer scale. And in addition, we can pump with the free-electron laser and then do a pump probe experiment where we have a narrowband excitation by the free-electron laser and do this broadband probing now on the nanoscale. The example I want to show you is some doped semiconductor nanowires, and these can be modeled by a Drude-Lorentz model. So basically there's a phonon line here, and then depending on the doping, there's a plasmonic resonance, which in the amplitude of a near-field signal gives such a dispersive shape. And it's sitting, the frequency where it's sitting is, the plasma frequency is determined by the carrier concentration, so the doping, and in the denominator where there's the effective mass. So these two things. And so we doped rather highly to have a resonance just in the spectral window where we have the best signal-to-noise ratio. So this is what it looks like. This is just an AFM image of such a nanowire. This is the spectrally integrated SNOM image. And then if we spectrally disperse, we see indeed this dispersive amplitude signal and then a peak in the phase at the plasma frequency, which in this case is around 1000 inverse centimeters. So now what happens if we do the pump probe? Now the signal to noise is much worse. I don't want to go into the details. But you can imagine that a pump probe experiment is more difficult to do than just with a static spectroscopy. Anyway, if we pump, then the red curve, this resonance shifts to lower energies. And we see this both in the amplitude signal and in the phase signal here. Here in this false color map, on this scale, we have the spectral information, the wave number, and here is the time delay. So this is before the excitation, the resonance is sitting here and then moving towards lower wave numbers and recovering back. And in the amplitude, one can see even better. Here's the resonance shifts to, here's the resonance in the unpumped case. It shifts towards lower frequencies and then recovers back as where FEL excitation is over. So here we plot the plasma frequency as a function of time. So it drops as we've seen before. And the reason why it drops is because the effective mass is going up. Because we use a terahertz beam, so we don't excite extra carrier. So the carrier concentration stays the same. So all the signal we are seeing is coming, the change in the signal is coming from the change in effective mass. And this is quite substantial, so it goes up by like 50%. The reason is that this is the band structure of gallium arsenide. So initially, carriers sit in this gamma valley. Here they have a low effective mass, and then if we heat up, they occupy the L and X valleys where they have a higher effective mass. So this is basically the physics behind this experiment. Now let's summarize again. These points we have discussed already. Now, with the last experiment, we could also demonstrate high spatial resolution in the S-norm. And the property of a free electron laser that allows us to do this is actually the high repetition rate. With S-norm technique with the oscillating cantilever, this needs a detection at frequencies in the 100 kilohertz range, which is the oscillation period of this cantilever. So the repetition rate of a radiation source has to be higher than this oscillation period. Otherwise, it becomes very difficult. So here we profit a lot from this continuous pulsing at a high repetition rate. And also for other experiments, of course, this is useful to get a good signal-to-noise ratio. But not all experiments work well at a high repetition rate. Namely, sometimes one wants to have a very high pulse energy to have a strong nonlinear drive, but one doesn't want too much average power because this would overheat the sample. As an example, if we want a pulse energy of 100 nanojoule with a really strong drive for many systems, but if we do this at 13 megahertz, then we have 1.3 watts of average power. This is quite a lot. Not many samples can withstand that, leave alone withstand without substantial heating that gives artifacts in the results. So what can one do? Well, one should reduce the repetition rate. But with a free electron laser, this is not easy because the repetition rate is given by the round-trip time of the photons in this laser cavity. So one can do pulse picking outside the cavity or cavity dumping, a picking in the cavity that makes pulses even more intense. This first one, this we do at Dresden-Rossendorf, this pulse picking outside the cavity. This one we are not doing. This is technically tedious. But there's even a more elegant way. One can have sources that don't have a resonator, and when one is free in the repetition rate. At Dresden-Rossendorf, we have such a source, namely the Telbe terahertz source. It's a super radiant source, so it's just an undulator, no resonator. How does it work? Well, if a electron bunch travels through this undulator, if the bunch is long, then it would emit incoherently, and this is not what we want. But if the bunch is shorter than the wavelengths we want to generate, then there's coherent superradiance, and then the power scales up quadratically with the number of electrons in the bunch. This is what we want for such a source. So it means, since the bunch compression is limited, in particular for high bunch charges, it means that in wavelengths one is limited to a lower frequency range. So it's in the lower terahertz range, basically. So Telbe goes up to 2.5 or 3 terahertz nowadays. The nice thing is that it delivers carrier envelope stable pulses, so we can directly follow the electric field in the time domain. So it gives us sub-cycle temporal resolution and amplitude and phase information. Here's a science example. Now we go back to graphene. If we excite graphene with an intense few cycle terahertz pulse, we drive a nonlinear current here. This is by heating and cooling of the carriers. It becomes nonlinear. And when a nonlinear current leads to a re-emission of terahertz radiation at the fundamental frequency, but also at the odd harmonics. The odd harmonics comes from the symmetry of the problem. So here are experimental results. This is the fundamental pump field, and third harmonic, fifth harmonic, even seventh harmonic we see, and we can follow this power scaling here. So with this, I come to the end. So we've seen that infrared free electron lasers provide terahertz for infrared, mid-infrared radiation in short pulses, tunable narrowband radiation, high peak intensities, high repetition rate, and this is good for high spectral resolution, resonant excitation, high temporal resolution, high field physics with the high intensities, and the high repetition rate is in particular good for the achieving high temporal resolution with this X-norm technique. On the other hand, there are super radiant sources that have very attractive features such as adjustable repetition rate, high peak intensity, and carrier envelope stable pulses, but they are limited to the lower terahertz frequency range. So a natural question is, can we combine this? And this is a future development. The planned DALI facility, DALI stands for Dresden Advanced Light Infrastructure. This should be the dream source, namely it should give CEP stable pulses in the terahertz, but also in the mid-infrared frequency range with adjustable repetition rate, and this can be achieved by a novel structure of combining free electron lasers and undulators. And this radiation source should be combined with advanced probing such as ultrafast electron diffraction to see the crystal and molecular structure, and angular-resolved photo emission spectroscopy to look at band structures. With this, I'm at the end. I listed the number of people here who contributed to the experiments I showed you and who are great discussion partners in our daily life. This is the spectroscopy group here, and I thank you very much for your attention.